Hi, let's now continue with the chain rule and how we can compute gradients in our neural networks. So we saw in gradient-based learning that gradients are of course core in computing updates for our neural network parameters. So what is exactly a gradient? A gradient is a vector that contains all the partial derivatives of our function with respect to a vectorial input. And it's a generalization of the derivative when our input has more than one dimensions. As a simple example, let's assume that we've got the sign computed on top of our vector input x. Then to compute the gradient, we simply append or create a vector where each of the dimensions has the derivative of the sign with respect to each of the dimensions. So cosine of x1, cosine of x2, and so on and so forth. The Jacobian is a further generalization of the gradient. The difference now is that we've got more than one dimension, not only in the input, but also in the output. So the Jacobian is a matrix which contains all the partial derivatives of all possible combinations between output and input combinations. And in column-wise, we've got all the possible outputs, whereas row-wise, we've got all the possible inputs. It is a generalization because when we have a single input and a single output, we just need to have like the top left corner. If we have multiple inputs and a single output, then we've got the gradient in one row. And with multiple inputs and multiple outputs, we have the standard Jacobian. Now we're moving from single elements to vectors, but we might also be interested in computing gradients with respect to matrices or even higher order dimensional objects like tensors and so forth. And why would we want that? Well, in a neural network, we might have actually such tensors, right? Like we can have more than 2 or 3 or 4 dimensions in our inputs. Our batches are giving us an extra dimension for our computations, so in general we might want that. And soon things become really complex when we start appending dimensions. How do we take transposes? How do we multiply things? We don't really have matrices per se, no more. So in these cases, quite often it makes more sense, or at least it's more comfortable, if we use the index notation. So if our, here in this example, we've got a simple function of like the linear module, right? So y is equal to the x times the w transpose. So our y function has n dimensions, or, like let's assume now for simplicity that our s equals to 1. So we've got n dimensions and our x input has m dimensions. Then the weight matrix is n times m. Right. So what does index notation stand for? Well, we take the partial derivative of a random output dimension. Let's say hi over a random input dimension. So xj, let's say. And yes, so this represents, let's say, a random pair of input and output dimension. And if we can derive a formulation for this random pair, it means we've got the formulation for all possible pairs, and then we can create a general construct that we can represent with matrices or tensors, or we can simply code it directly in our software. So, for instance, in this particular example, let's say we want the partial derivative of the ith output with respect to jth input. So we take the operator, the partial differentiation operator, over our operation, linear operation, which is then we have to sum over. We expand here the inner product. So it is important to note here that we introduce now a dummy index which runs over all the elements in X and W and performs the multiplication. Now the J and I indices that we relied in the beginning are still present, right? So they represent these random but now specific indices in the output and the input that we're interested in. And the only extra dimension, index that we added was K it's a dummy dimension which runs over all possible elements in the respective matrix and vectors. Now, if we take one step further of this operation, we'll see then that the partial differentiation can apply only to, of course, the inputs for which there is the xj. And since it sets to 0 all the variables for which there is no xj, this means that we're going to have like this operation, right? So this means that here is a delta notation. So if our dummy index value obtains the value of j, which is our input here, then we have indeed a partial derivative of 1, and that's why we've used delta notation. And for all other k indices other than j, we've got a 0, right? So this means basically that we end up only with our Wij element in our matrix. So this means that if we generalize it over all, over all possible combinations in our Jacobian, this is our matrix W. Note here that here we don't have the transpose of W, but W, and the reason is that here we were, in this location, we were taking the multiplication of the row, of X with respect to the rows of W. Intuitively, Jacobians and gradients capture always the same thing. Basically, what is the effect, what is the change in the output with respect to the change in the input. And all these quantities are linear operators that capture this simple quantity, which means that if you have different types of shapes, so not matrices or vectors anymore, our tensor Jacobian would again be capturing exactly the same quality, only with a different shape. So if our input shape is not like a single vector or a matrix, but it's a higher order tensor, then our final Jacobian will be a tensor, another tensor, with the shape of the output times the shape of the input. In this case, perhaps it makes sense, or it's more comfortable to use the Einstein notation instead of matrix multiplications. So Einstein notation is like a notation that makes things more easy to read and write. So if we have, for instance, the y equals, let's say, a1 x1 plus, so ai xi. So a1, let's say from I equals to 1 to 3, up to 3, a2 x2 plus a3 x3. In Einstein notation, we just use the I index, as a subscript and a superscript for the two variables, and this indicates a multiplication for each I and then summation. And basically this can represent also the multiplications and summations that take place between vectors or matrices, but using the Einstein notation we can generalize to any type of index or combination of indices in higher order tensors. Now that's quite easy because when you've got higher order tensors, it's not clear what do we mean by multiplication. So if we use a multiplication sign, it's not clear which index gets multiplied and summed with what index between the two tensors, whereas with the Einstein notation we can make this very explicit. This is particularly useful, especially when we're programming our operations. Geometrically, it's very nice also to understand what the Jacobian stands for. So the Jacobian actually represents the best local approximation of how the space changes when we're applying a nonlinear transformation. So our space, our input space is x, right? And then we apply a nonlinear transformation f on top of it, or h on top of it. So this, of course, changes the input space x into f of x. The Jacobian represents how this change, change takes place. It's since Jacobian is a linear operator, it only makes sense locally, so in a small neighborhood around a particular location x. And it's the best linear approximation around that. You can also think of it intuitively as the generalization of the derivative. The derivative is also the best linear approximation of a curve, right? So when we take the tangent, we can approximate what happens around that particular point where we're taking the tangent. What happens on the curve, we can approximate with this tangent, with the derivative. And the Jacobian determinant actually gives us a similar quantity for the amount of change that happens. So not just what kind of change, but the amount of change. Specifically, the Jacobian determinant computes the ratio of the areas before and after the nonlinear transformation. So the blue squares here, the blue area here represents the, how the change, how the input space changes, how the space changes. The red box here is the unit, let's say, square, and in this picture it represents how the unit square changes after the nonlinear transformation. And as we can see here, the Jacobian is a rectilinear shape that tries to approximate the red one. And its size is captured by the Jacobian determinant. It's very similar to the absolute slope measured in the 1D case. We use the Jacobian in the change of variables and in normalizing flows. So some basic rules of partial differentiation are also included in this slide for your help, but you can find all these things online and also in the Mathematics for Machine Learning book that I referred to in the first lecture. Now, when we have more complex functions like the chain rule, we can use the chain rule. Specifically, the chain rule basically decomposes the total gradient, the final gradient for one function, to a multiplication of partial derivatives of the functions that compose the total function. So if our function is comprises L nested functions, then dh over dx equals to the dh over dhl times dhl over dhl minus 1, and so on and so forth until we arrive at the input. And in this expression, each of these guys here is basically a Jacobian gradient, whatever you want to call it, vector metric tensor. And clearly, when we want to compute the final gradient, so that's going to be the final gradient for our parameters, let's say in our neural network, we have to make sure that each component matches dimensions. If it doesn't, if the dimensions don't match, basically this operation is not valid. Like there is something wrong there. Intuitively, what does the chain rule and the tensor stand for? I think that's nice to understand because, again, when we are moving to tensors, things start becoming less intuitive. So when we've got vectors on matrices, this expression is actually quite straightforward. It's just matrix multiplications, but with higher order tensors, things become a bit more involved. Again, for the simple 2D case, it's a matrix multiplication. So let's start with that. Let's say that our function h has m inputs that come from g and n outputs, and our function g of x has k inputs because of x and m outputs, right? So then this dimensions match, right? So n times m and then m times k. So indeed, the gradient or the Jacobian of our final function with respect to the input, dh over dx, is a Jacobian matrix of n times k. Yes, so n times k. Now, what does the Jacobian do here? The Jacobian captures again the change in the output with respect to all possible changes, with respect to the changes in the input, so all possible changes. So let's say that we're focusing on one of the dimensions of the output, like here, the blue guy here. That corresponds to this random row, and it's 1 out of k. So 1 out of k features, 1 out of k input features. So we want to see now what exactly is the effect to this particular output dimension with respect to one very specific input dimension out of k. Now, to compute this blue guy, we have to visit the same row in the intermediate Jacobian matrix, dh over dg. So basically, this Jacobian matrix measures how sensitive h is with respect to any possible changes of g. And why do we say any possible changes of g? Because our input x, every dimension of input x, affects all possible outputs g. So this is the whole row that we're interested in. Maybe I should use the green color, right? So this is the row in this Jacobian that corresponds to all effects that specific x1 have, all the x1s have. Then we multiply it with all x1s, and we arrive at our result. So again, in the chain rule, what we compute per dimension in the end is basically a sum over all possible individual changes. We have to branch out over all possible changes in our respective inputs, and then by doing like summing over and multiplying accordingly, we obtain our final partial derivative. Now, why do I say that? Because when we have higher dimensional tensors, it's exactly the same thing. Nothing changes, right? So when we've got here a batch of S, so we have to append one extra dimension. The only thing we do is that we do a mental switch, and we replace this row here with a matrix or with a tensor, nothing else. So other than that, the operations that take place are exactly the same. And this is why I mentioned before Einstein's notation, because with the Einstein notation, we can perform this mental switch very easily. We just replace the operation, like one index with a pair of indices, or with 3 indices, and that's it. And now a visual example of how the chain rule works. So let's say we want to compute one again of our partial derivatives, so x1, with respect to an output. So in this case, our output is a scalar value. We have to compute all possible paths, so the red one and the blue one, and then we sum. So again, we have to compute all possible changes that happen to h from a single input variable x1. And by doing so, we can compute its partial derivative. And the same thing happens for x2, and you can also move to x3, x4 if there is x4, and so on and so forth.